We have another searching algorithm similar to binary search called ternary search. With ternary search, instead of dividing the list into half at every step, we divide it into 3 parts. So here we have 2 middle points, mid 1 and mid 2. Let's see how we can calculate the index of these middle points. First, we have to calculate the size of our partitions. What is the size of these partitions? You might say it's equal to the length of the array divided by 3. Well, that's correct, but only for the first step. As we narrow down our search, our partitions also get smaller. So here's the proper way to calculate the partition size. Right minus left divided by 3. Now we can calculate the index of these 2 middle points easily. Mid 1 equals left plus partition size, and mid 2 equals right minus partition size. Once we identify the middle points, we need a few comparisons to find the target value. If it's not one of these middle points, it could be in one of these partitions. So we'll repeat all these steps for that partition, exactly like binary search. Again, we can implement this using recursion or iteration. Now, what's the time complexity here? It's log base 3 of n. What is this base 3? Well, let's take a break from programming and go back to math. Look at this equation. 2 to the power of x equals 8. What is x here? It's 3. Logarithm is a function that helps us find this power. So log base 2 of 8 equals 3. In other words, logarithm tells us to which power should we raise a number to get some other number. So log base 2 of 8 tells us to which power we should raise 2 to get 8. Now what about log base 3 of 8? It's like asking to which power should we raise 3 to get 8? The answer is 1.89. So both binary and ternary search run in logarithmic time, but in binary search, the time complexity is log base 2, whereas in ternary search, the time complexity is log base 3. So does that mean that ternary search is faster because log base 3 of a number is smaller than log base 2 of that number? The answer is no. Here's the reason. With binary search, how many comparisons do we need at each step? 3 comparisons. We have to check to see if the target value equals the middle item or if it's greater or smaller. Now with ternary search, we have to check to see if the target value is greater than the second middle point or equal to the middle point or less than the second middle point and greater than the first middle point or equal to the first middle point or less than the first middle point. Jesus, so many comparisons. So that's 5 comparisons in each step. We can mathematically prove that the total number of comparisons to find the number in the worst case scenario is more in ternary search. How we do that is beyond my knowledge and the scope of this course. But what you need to remember is that binary search is faster than ternary search. In fact, as we divide the array into more parts, our search algorithm gets slower. What if we have an array of 10 items and we divide the array into 10 parts? We'll end up with linear time complexity because in the worst case scenario, we need to compare the target value with every item in the list. All right, enough theory. Now I want you to implement ternary search using recursion. The implementation is very similar to binary search, except that you need a few more conditional statements.